We are now recording our second talk of the day today for the last session of the semester, the Future Leaders in Robotics and AI Celebrating Diversity and Innovation Seminar Series, sponsored by Microsoft DC Metro Engineering Site. This is a joint effort of the Maryland Robotics Center at the University of Maryland and Microsoft DC Metro Engineering Site. All of the videos from our talks are available at robotics.umd.edu/futureleaders, or you can find them on the Maryland Robotics Center website page. I am also excited to introduce our second speaker of the day, Thomas Berrueta. And Thomas Berrueta is an interdisciplinary researcher and PhD candidate at Northwestern University's Center for Robotics and Biosystems. His research is at the intersection of statistical physics, artificial intelligence, and robotics, and he likes to explore the consequences of agent embodiment on learning and control across length scales. Within that kind of scope of things, he seeks to make autonomous systems more adaptable, robust, and lifelike by exploiting randomness and uncertainty in ways that parallel biology. He is the recipient of Northwestern University's Presidential Fellowship, which is the highest honor bestowed on to a student. So without further ado, Thomas Berrueta, please take it away.
Let's see. Can everyone see my screen? Great. Thank you very much for the nice introduction, Michael. And I would like to thank you all for inviting me to contribute a talk to this great seminar series. I'm very excited to be here. As Michael said with this kind of introduction, my name is Thomas, and I'm from Northwestern Center for Robotics and Biosystems. And throughout most of this talk, I'll be focusing on some recent work that I did in reinforcement learning. As the previous talk was kind enough to share, reinforcement learning can often be kind of tricky to get right with embodied systems. If you have ever done reinforcement learning work, you might have seen videos or produced videos that look kind of like this, where you have robots do all kinds of silly things. These are Majoko simulations. Right on top, what you're looking at is the ant environment in the Majoko simulator. And the ants are kind of going crazy. They're doing these nice cartwheels, and they look really fun, and I like it, but I wouldn't trust these robots to be around me. Right. And so in order to take advantage of the massive representational power that reinforcement learning gives us and deploy it into the real world, we need to be able to sort of find a way to tame reinforcement learning and make it more reliable and transparent so that it can be safely around people. But before I really get into all of this, I'm going to give you a brief overview about who I am and what it is that I do. As a roboticist, I'm largely interested in studying this question of embodiment and the ways in which it can inform or impact learning, design, and control. And of course, this naturally involves a lot of different fields of study, which I've listed some of which here on the page. And I've been blessed to contribute to a lot of these fields across a lot of different publications that I've done over the years. I'd like to sort of give you a brief glimpse into each one of these areas. Something that you'll note on this slide here, as I've divided it up into design, control, and learning, is that this actually, design, control, and learning, induces a nice hierarchy as far as length scales go. So when we're thinking about meter scale systems, large scale systems, we're thinking about the levels of computation, the things that are available to them. They're capable of doing quite a bit, right? But however, let's say that now we have simpler robots, smaller robots, such as these centimeter scale swarms that you're seeing in the middle of the slide. They might not be able to do powerful deep learning things. Instead, they're sort of in the position that they have to just do control. And then, of course, whenever we go even smaller at the micron scale, each one of these little microparticles is thinner than the width of your hair. So they're quite small. They're extremely limited. The only things that we can really do is design, right? And so now I'd like to jump into one of these systems first. One of the things that I've spent a lot of time doing during my PhD is figuring out how it is that we can formalize the physical properties of complex robotic systems and harness them for control. So to explain a little bit of what you're looking at here, this is a tabletop robot collective capable of phototaxing, so that is moving towards the light, by manipulating its internal collision distribution. These little robots are called smarticles, and individually they're useless. They don't really do much. But collectively, they can bang around each other and induce this sort of diffusion-like locomotion that they get out of this ring. And so what I was able to do in this work is figure out how it is that we can exploit the statistical mechanical principles that govern the dynamics of the system towards getting persistent locomotion. And this means effectively biasing the collision distribution. And across a pair of publications, we developed a novel theory that I'm listing here of statistical mechanics that explains in general why emergent behaviors such as this one, but also emergent behaviors such as these emerge in a broad class of systems. And we call this thing rattling theory. And this doesn't just apply to robotic systems. You can take an active matter system or perhaps some biological systems, and this theory sort of tells you how it is that statistical correlations among the degrees of freedom of some complex system give rise to self-organization. And it's principles such as these that I like to find in robotic systems and find ways how to use them for control. But one of the nice things about formalizing physical principles in this way is that once you have such a formalization, you can make direct use of them during optimization, which can be super useful for robot design. And this is another one of my focus areas. I like to figure out how it is that I can encode physical intelligence, so to speak, in robot morphology and robot design. And what you're looking at right now is a colloidal collective of microparticles undergoing coupled chemical reactions that result in these very complex dynamics that you're seeing. And as I said earlier, while big robots have access to big amounts of compute and they can exert fine-grained control over their actions, none of this is true at these tiny, tiny scales. And so instead of control, we often have to think about how it is that we can use design to get the intelligent outcomes or task accomplishments that we desire. And this is often framed under the umbrella of what's called as physical intelligence. And so actually using the same theory that I developed in the previous work, the rattling theory, I was able to optimize the rates of reaction of this system that you see right here and induce nice emergent collective behaviors such as the ones that you see over on the left-hand side of this video. And then what's most remarkable about it all is that due to the electrochemistry of these reactions that you see here, these particles aren't just oscillating in this beating motion, they actually are generating in an oscillatory way as well currents directly on board these particles. And so now we have access to alternating currents these particles are generating, and what we can do is harvest them and use them to power micro-robot arms, which is exactly what I'm showing you over on the right-hand side of this page. And, I think that this example really nicely illustrates what we stand to gain by designing for physical intelligence. I bet that you wouldn't have looked at the system over on the left-hand side here and guessed that it could be used to power a state-of-the-art micro-robot arm. And so that brings us to learning, which will be the focus of the rest of the talk. And I'll be talking about systems and simulations such as this one, but also I want to note that we are working on physical experimental implementations of this work as well. And in particular, I want to focus on reinforcement learning and this manuscript that we just had accepted at Nature Machine Intelligence. In fact, you should be able to see it next week. We're very excited about it. But to briefly summarize the RL framework, it's a data-driven framework for solving sequential decision-making problems. So RL roughly sees the world in this way. You have a policy which observes the state of the world at this current moment in time, designated by X, and then it produces an action U with which it hopes to advance the state of the world through its dynamics towards the next state, XC+1. And ideally, what we're trying to do is find a policy that optimizes the expected cumulative rewards, which is this expression that you see right here. And really, all that matters here is that this is the way that we're going to encode a task, right? And so we're trying to design policies that optimize objectives such as this one. Something that I think is really important to keep track of is that the sequential nature of this decision-making problem can be better seen when we visualize the reinforcement learning process in this way. So let's say that you do choose a policy. The net effect of the policy really is that it steers your states along specific paths, right? Ideally, you're going to design a policy such that the states, the paths that your robot heads down are highly rewarded states. And this is exactly sort of the intuition that I want you guys to have as we follow along with the rest of the talk. By now, I probably don't need to do a lot of work motivating the overall power of reinforcement learning, but here's one of my favorite videos. This is from a team in Korea that they developed a reinforcement learning agent capable of beating a professional women's curling team. And while there's a lot of other demos that you might find very impressive as well, I really like this one specifically because they went the extra mile, not just of developing an experimental system, but also for finding professional curling players against which to play and then beat, right? So despite all of these incredible achievements that reinforcement learning has, there are key shortcomings that still prevent it from being widely applied in the real world. And to offer a few of them, I'll list a couple. First is their reliability. It's kind of well known that reinforcement learning agents are somewhat unreliable in the sense that they are sensitive to their initial conditions and the way in which the models are initialized, right? Ideally, we would just have a robot that we place in an environment and we expect it to work. The other issue is that we know that it takes a lot of data in order to get a reinforcement learning agent to do the task that we want them to do. And so sample inefficiency is a big issue. You can't just have an engineer herding a robot around trying to demonstrate the same behavior years and years on end, collecting data. to get only unreliable performance at the other end of it. And then lastly, but interestingly, RL algorithms are typically best suited to these episodic tasks, right? And these are tasks that you can sort of attempt over and over again via trial and error. But of course, the problem is that outside of, say, warehouse environments, there's not necessarily a lot of tasks that naturally have this problem structure. Sometimes we just want to deploy a robot in the real world and have it, figure out how it is that it should be solving a task, and not have an engineer have to reset the environment and have the robot attempt it again and again and again, or even worse, build an automation system around it so that this is all automated. So nested automation in this process. And what's remarkable, as we show in this recent paper, a lot of these issues, in fact, all of these issues that I'm listing here, can actually be tied back to violations of the IID property. This is a very fundamental thing. So what is the IID property anyway? The IID property is likely the most widespread assumption in the field of machine learning writ large, and almost every algorithm requires it in one way or another for guaranteeing its performance. And it stands for independent and identically distributed. So let's say that we have data samples xt drawn from some distribution p. For this data to be identically distributed, it's quite simple. It just means that, in your batch of data, all of those samples must be drawn from the same distribution. We're just going to assume that that's the case. And this is something that is often either true or not true, depending on your problem setting. And it's kind of hard to do something about this. Then the independence condition is this one right here. So let's say that I'm asking you about the joint probability of the data sample or the batch of data that you've collected. Then if that data set is independent, then the distribution factors along the individual samples. So basically, the probability of sampling, say, data point x1 cannot depend in any way on the probability of sampling the point x0, right? And so basically, probability samples in this way, factors in this way. Great. So why is this an issue for reinforcement learning? Let's say that our data is distributed according to the following distribution, and let's say that I draw 2 samples from it. If these are IID, then we know that they satisfy this following relationship. So basically, we have the 2 data points that factor, as I said before, but then simultaneously, actually from the axioms of probability, the following relationship must be true. This is basically the definition of conditional probability, right? And so if the data is sampled IID and the axioms of probability are going to hold, then we need to have this term right here effectively simplify to xt. And so why is this an issue? By now, some alarms should be going off in your head about this term, because in a sequential decision-making problem, this quantity right here effectively represents the dynamics of the sequential decision-making problem. And in robotics, this might literally represent a path that your robot has to follow. And in the reinforcement learning setting, as I was showing you earlier, what this means is that, when we strap a policy onto our agent, it means the set of paths that we're following with the agent. So in general, this quantity does not actually simplify down to just the sample alone. And so this is an issue. But it turns out that this is not just an issue with reinforcement learning, and instead it kind of reflects a broader truth about doing any kind of learning with data sampled from embodied systems. And so while we might be able, in principle, to overcome some of these issues in disembodied RL systems, they are unavoidable in embodied systems like this one right here. And this is, of course, because to be embodied is to have localized experiences that unfold continuously in space and time. Let's say that your agent satisfies Newton's laws. Then if you do, then those agents' trajectories are going to be inherently smooth. And that means that they're going to be correlated in a way that is sort of objective in a sense and unavoidable, right? And so, okay, correlations are now unavoidable in embodied systems. Can we do anything about this? I think that we can. And the question that we need to be asking is, how decorrelated can we make the embodied experiences of agents? And this is the technical approach that we're going to be taking now. So to answer this question, we must reason about agent experiences as continuous streams of experience or trajectories sampled for some Markov process, right? And for any given agent, we can describe the probability distribution over these streams of experiences as a probability distribution over their trajectories or their paths. And what I'm illustrating here in this robot is a given path within the support of that path distribution. And what the support is basically anywhere that the probability distribution is greater than 0. And so this effectively implies anywhere that it's possible for the agent to go, right? And so because our goal in this problem is to find a trajectory distribution that describes the least correlated paths possible at all, right? Not for a specific dynamical system, but in general, we're going to be taking inspiration from the literature in statistical mechanics, and we're going to maximize the entropy of this path distribution, which effectively looks like solving a problem like this, and hopefully getting out of this a path distribution that looks like that, where you can see that the support of the distribution has now spread all over the domain, and basically the agent is more likely to experience a greater diversity of experience. So their paths are a lot less correlated than one another. However, if we solve this optimization naively, we're not actually going to get a distribution over continuous paths, right? In fact, like the true optimum of this problem is IID sampling, discontinuous sampling of your data. And so we need to find a way to formally encode this idea of continuity of experience as a constraint in our optimization. And it turns out that we can do that. And it also turns out that it is quite complicated. And I don't actually have the time to break this down completely in detail for you, but I like to sort of walk you through the big, broad intuition. So the first term here in this optimization is just your entropy functional, where the only change that we're doing is that we're now integrating over paths and not over states or configurations. Then we need a normalization constraint, because whatever this path distribution looks like, it has to integrate to 1 in order for it to be a valid probability density. And then lastly, this is our continuity constraint. And effectively, what this is doing is it's bounding the volume of states reachable by an agent from any given configuration to be finite, right? And so effectively, this means that your agent is not allowed to teleport. Great. Despite how scary this problem might look, it actually turns out that there is an analytical optimum to this problem, and it's this one right here. And this is what we refer to as maximally diffusive trajectory statistics, or MaxDiff trajectory statistics. And they have some really nice properties that are important to discuss, and so I'd like to list a couple of them for you. So the first question you might have is, why is diffusion in the name? Well, it's because this probability distribution actually belongs to the trajectory distributions of a class of diffusion processes. And so this means that the least correlated state transition dynamics are actually given by a diffusion process. And so let's say now that I use MPC and I take some dynamical system and I force it to satisfy these statistics. So here I'm showing you a 9-dimensional non-smooth dynamical system that I'm asking to achieve MaxDiff statistics in the X dimension, right? And what we see here is that when we do this, our agent now all of a sudden is achieving path statistics that are statistically indistinguishable from Brownian motion, some pure diffusion, right? And why is this a good thing? Well, diffusion is exploratory in nature, which means that when we're doing reinforcement learning, this is going to give us benefits to sample efficiency as well as data diversity. Diffusion is, in a sense, space filling. It expands and it evolves, and if you put it in an empty environment, it'll fill up that environment. So what I'm doing now is taking that same robot that I showed you in the previous slide, and I'm deploying it into this N environment with some control barrier functions so that we don't run outside of the walls. And then we're just satisfying MaxDiff statistics without any other objective. We're just encouraging MaxDiff statistics. And what you can see here is that we're filling up the N, right? And that's very nice. That's exploration. It encourages path diversity. This also works in more complex environments, such as this one. This is a floor plan, which is great. However, the most important property of maximally diffusive trajectories is that they are ergodic. And so ergodicity is a very complex property that I don't have the time to fully break down for you, but I'm hopefully going to be able to give you an intuition. Effectively, what it means is that the statistics of any individual infinitely long deployment of an agent that is ergodic will be equivalent to an ensemble of deployments. Okay, so let's say that we're putting together a data set from the experiences of an agent, right? We're going to sample from the underlying distribution. Let's say that in one case, we just have direct access to the underlying data distribution that we want to sample from. And so we just draw samples IID. That's the multiple deployments case. And then separately, let's say that our sampling strategy is to take our robot and have it follow an ergodic trajectory in that environment. And we're going to sample only along the trajectory of the robot. This ergodicity implies that if we let the individual trajectory of the robot go long enough and we keep collecting data from that trajectory, that the statistics from the data set built from this single trajectory are going to be identical to the ones for the multiple deployment. And this is really nice because the multiple deployment setting is effectively indistinguishable from IID sampling. And so this means that ergodic sampling is the same as IID sampling statistically. And so this means that even though our agents are sort of fundamentally correlated in their experiences, we can get around these issues via ergodic sampling. Okay. So in order to figure out how it is that we can apply this idea into reinforcement learning agents, I developed the following optimization objective, which augments the reward function, the standard reward function in a reinforcement learning setting with this term right here, this log ratio term that you see. And of course, once again, I don't have the time to really derive this for you, but what you should be thinking about here is that this term effectively minimizes the KL divergence between your agent's current path statistics and the maximally diffusive statistics, all the while solving the task as well. Great. And so this is what we're going to do. This is the strategy that we're going to take. And so now to benchmark this approach, we're going to be using spatial navigation tasks in Machoko, which are these ones that I've shown you before. But what you should be really thinking about is this robot right here, is acceptance simulation. That's the inspiration for all of this. And we compared against state-of-the-art alternatives, MPPI and SAC in green and blue, respectively. And now in the following couple of slides, I'd like to show you two very important properties that MaxDiff RL agents have through these empirical videos. Okay, great. So now what you're looking at is a simulation of the swimmer benchmark run by MaxDiff. So the first property of MaxDiff RL agents is that it's provably reliable. Ergodicity guarantees that the performance of MaxDiff RL agents is not affected by either initial conditions or random initializations of the model. Okay, so if we take a look at the performance curves of these agents that I'm showing you in this very video, these are the curves for MPPI and SAC. So I would say that the MPPI curve is pretty representative of what what a standard reward curve looks like in RL. It's high performing, but it's got this big broad variance band. In stark contrast, this is what ours looks like, right? So we have this near zero variability in the performance of MaxDiff RL agents. And so basically this means that MaxDiff RL agents can succeed at their task regardless of initial condition. And this is something that you can see by looking at the video and how closely packed all of the MaxDiff RL agents are in purple. The second property of MaxDiff RL agents that I want to make sure I highlight is that they are capable of solving non-episodic tasks. And so this is what we also call single-shot learning sometimes. The idea here is that we want to set the agent down in the environment, and we want to let it just run and learn as it's going, as opposed to just resetting the task over and over and over again. And this is once again another property that we inherit from the ergodicity of maximally diffusive trajectories. Effectively, if a MaxDiff RL agent can solve the task at all in multiple deployments, then it can also solve it in a single one as long as it's long enough. And the video here, what I'm showing you is the evaluations of MaxDiff RL policies learned in the single shot setting, right? And as you can see, we're still highly performing while the other algorithms struggle a little bit more to do this in this non-episodic environment. And the reward curves look like this once again, where we retain this sort of near zero variability in our performance, and MPPI and SAC perform in a similar way. So throughout this talk, I've made the case that we should be thinking about the ways that embodiment affects learning. And in particular, I explored the ways in which embodiment leads to violations of the IID. These can have an impact, of course, on the performance of RL algorithms. And importantly, I shared MaxDiff RL as a solution to this issue. MaxDiff resolves the IID issue. It promotes better sample efficiency. It leads to more reliable performance and non-episodic task success through its ergodicity, all the while achieving state-of-the-art performance. In future work, we're very excited to try to take this into the real world. This is very early video of a platform that we're developing for doing this. But to leave you with a final sentiment, reasoning about embodiment, how it affects learning processes, can be very productive. And I believe that it can lead to more transparent and reliable RL agents in the future. And I'm very excited to see where the future of this work leads. And so before I wrap up, I want to acknowledge my collaborators, specifically Ali Panoski, who did a lot of computational work for the study, as well as my advisor, Todd Murphy, and the other collaborators involved in the previous videos that I showed you, as well as my funding. And now I'd be happy to show you some, I'd be happy to answer some questions. Thank you.
Hey, thank you. You have to make do with just us clapping up here right now. But thank you for the wonderful talk. If anybody has any questions, please put them. Oh, great. We have a question there. So the first question is from Malcolm McLever, which asks, any bound on the variance in the low sample limit with MaxDiff RL? I did see it was high, though lower than conventional algorithms in the early stages.
we don't yet have any formal results on sample complexity specifically. So this is something that we're interested in exploring. How does the actual sample complexity of the algorithm evolve as a function of how long you run it in these ergodic trajectories? The problem, of course, is that doing these kinds of analyses with black box neural networks, it's kind of hard. We were able to provide guarantees in this setting, largely because we're using theoretical analyses that get around, and they don't directly address the neural networks themselves, but they get around them. They provide sort of like bounds on the performance outside of the black box.
Right. So I had a question, which was this continuity of experience seems great, but it also seems to make the problem more difficult. A lot of times we use kind of like a Markov assumption to say, like I don't have to worry about that. And it seems like kind of the very opposite of that in some sense. So what is the kind of secret sauce? Maybe highlight a little bit for me to make that tractable again.
Yeah. So of course, so that objective that I showed you earlier, this log ratio between the distributions, you're very right to point out that it's very challenging to compute this question. It's sort of intractable. So the secret sauce is that I actually derived an analytical approximation to this objective that is done empirically using covariance matrices and logs and determinants. And this is something that you can do, if you have it's linear in the length of the like number of samples. So it's the number of samples that you take, but it is squared or cubed depending on one assumption that you make on the dimensionality of the state. So if you're dealing with extremely high dimensional systems, it definitely can get messy, and there are other shortcuts that you can take to sort of improve on this. That being said, I think that like it's nicely tractable with this approximation. They agree at the optimum, but they are different in the neighborhood of the optimum.
Okay, great. Thank you very much. I have one more question, and I think like feel free to say this is like, too high level of a question or something like that. But I really like the rattle theory sort of stuff you showed at the beginning. It's just a very kind of very cool factor thing. So I was wondering, what is the coolest rattle theory sort of result in an embodied system that you have like worked with or seen or know about?
Yeah, okay. So I love this question actually, because I did a lot of work with rattling theory that didn't necessarily lead to productive papers or something like that, right? And so I did a lot of really silly experiments. We had this experiment with the same SmartIcle system where we were trying to manipulate the different self-organized states of the system. So these low rattling states, right, that spontaneously evolve. There's like a finite set of them for any given complex system that you have. And so we were trying to use planning between these self-organized states to achieve some sort of like task relevant behavior. And something we tried to do is we sort of put SmartIcles in a jail, so to speak, and we tried to manipulate the different self-organized states to have them break out of jail. We called it the jailbreak experiment, and I do have a fun video of that somewhere in my computer, but it did not lead to a paper because the technical contribution can't just be a fun video.
Yeah, but fun videos are still fun to watch. I'd like to see that sometime. Anyway, thank you very much. Let's thank our speaker again, and thank to both of our speakers. So this concludes our final set of Future Leaders in Robotics and AI Celebrating Diversity and Innovation Seminar Series talks for spring of 2024 semester. Thank you to everybody for joining us. This has been sponsored by Microsoft DC Metro Engineering Site, and it is a joint effort of DC Metro Engineering Site from Microsoft and the Maryland Robotics Center at the University of Maryland. So thank you, everybody. And we will hopefully see you again next year.